Hey, hello guys. Welcome to the NR live stream. Today presentation was given by Sharon. He's from Pittsburgh Goa campus. Thank you, Sharon, accepting our request. Please continue your presentation. Thank you so much.
Hello, good evening, everyone. Myself, Sharan Hiramat, a research scholar from BITS Pilani Goa campus. Today here I am presenting a small talk on my topic carbon nanomaterial based fluorometric detection and scavenging of toxic analytes, including heavy metals and small molecules. So here in this I have written heavy metals and small molecules, but apart from that, our work is also extended to the biosensing materials. Okay, so here I am presenting that biosensing part of the work. All right, moving on. We all know recently the fluorometric methods for detection of analytes has received enormous attention. So in this regard, there have been many fluorophores which have been developed, which are being synthesized, and in that the organic based molecules are being of the great leaders. But during the last decades, the fluorescent nanomaterials have gained lot of interest, and they have been one of the uh, ingredient part in the fluorometric sensors which are coming up recently. So I am here talking about one of them, that is carbon dots, carbon nanodots. They are also known as carbon nanodots. So here we are discussing specially on fluorescent carbon dots, and in the fluorescent carbon dots there are many varieties. For example, the carbon dots which are prepared from the organic molecules, carbon dots which are prepared from the biomass, and carbon dots they are prepared from graphene or graphite based molecules, as well as the graphene nitride molecules. Now here the carbon dots which are being synthesized from the green mass or the biomass, that are being specially explored during the last few years. So because as they are synthesized from the biomass, they are highly water soluble, and they show more fluorescence with high quantum yield, low toxicity, and excellent biocompatibility. For many of the biosensors, the biocompatibility or the toxicity levels are one of the significant parameters, and they and these properties are extensively used in the applications like catalysis, sensing, biosensing, bioimaging, and so on. So here I am showing you one of the simplest scheme for the synthesis of fluorescent carbon dots. Here we can see from the thermal method, hydrothermal method, we can use orange, watermelon, potato pulp. We can also use waste food as the green source or the carbon source for the preparation of carbon dots, and they are at different temperatures according to the size, according to the properties, according to the excitation as well as the emission wavelength of the particles, carbon dots. We can vary the temperature in the hydrothermal method. Then we can go for dialysis for the filtration, and we'll get the fluorescent carbon dots. So these carbon dots can be prepared from green materials, and they avoid organic molecules, and these two will ensure the synthetic method is very cheap and it has low toxicity. Now if we come to the sensing part of these carbon dots, along with carbon dots, here we are using MnO2 nanosheets, manganese dioxide nanosheets. So if we talk about MnO2 nanosheets, they are two-dimensional structures with high environmental compatibility, and they are high surface area. And these MnO2 structures, they come with different structures like nanosheets. They come as square plates, nanorods, nanotubes, But here our interest is with nanosheets because as they provide large surface area. Because of their large surface area, they can be highly used as nano quenchers, and nano absorbents are also used as catalyst. Now, with combination of CDs and the MnO2 nanosheet, we can obtain a FRET based sensing platform. Now, FRET, F-R-E-T, Fourier resonance energy transfer. If we see the UV absorption of MnO2, which is between 300 to 600, and the fluorescence emission of most of the biosynthesized carbon dots is around 580 to 680. So within this, there is easy energy transfer from the fluorescent nanomolecules, fluorescent carbon dots to the MnO2 nanosheets. So with the same strategy, there have been many reports on detection of GSH, alkaline phosphatase, and organophosphorus, uric acid, ascorbic acid, biothiols, and many all. And now, as of now, we have also developed another sensing method for hydrazine, and now I am presenting the one which is of E. coli. Now, coming to the work what we have published recently in sensors and actuators. So a redox coupled carbon dots MnO2 nanosheets based sensory platform for label free and sensitive detection of E. coli. Here there are two important points to understand in the title itself. One is label free, another one is the sensitive detection of E. coli. Now, when it comes to label free, if you have come across any of the biosensors for generally for any of the bacteria or virus or fungus or the cancer detection, they especially they use some biomarkers which can directly attack our analyte. But here our method goes without any labels. Okay, so here if you see the mechanism here, now we have synthesized carbon dots, and on addition of MnO2 nanosheets, the fluorescence of the MnO2 nanosheets is being quenched because of the FRET. Now we have E. coli with the help of a redox couple between benzoquinone and hydroquinone. The benzoquinone after the reduction becomes the hydroquinone. This reduction takes place on the surface of E. coli, and now hydroquinone now goes and further reduces the MnO2 nanosheets. These MnO2 nanosheets after reduction will become Mn2 plus, and the sheet nature of the MnO2, it will break and fluorescence of the carbon dots will be released into the solution to give back the fluorescence. Now initially the CDs and MnO2, they due to the FRET, the fluorescence has been quenched. Next, due to the enzymatic reaction on the surface of the E. coli, the BQ, the benzoquinone, is converted to hydroquinone by 2 electron reduction, and this hydroquinone further reduces the MnO2 to Mn2 plus. Okay, now this Mn2 plus will settles down and CDs will release into the solution to give out the fluorescence back. This is the simple mechanism which we have adopted for the detection of E. coli. Coming to the resultant discussion, in that first we'll go for the characterization of CDs. Now, as carbon dots are being prepared by the potato pulp, we see many of the functional groups like COH, OH, C double bond O, and C double bond C. So we can see the IR peaks where the OH, CH, C double bond O, C double bond C can be seen. Then with the AFM, we have also seen the size of the particles. So there the size of the particles was around 5 to 10 nanometers. It was uh, further confirmed by TEM, where we have got around 5 to 6 nanometers of size for the carbon dots. Next, for the MnO2, we have carried out the UV study, where the peaks of KMnO4 are now being reduced to the peaks of MnO2. It shows that the KMnO4 has been transferred to MnO2, and also AFM shows the sheet layer as each sheet have a thickness of 5 nanometers. And further, for the fret, the carbon dots have to come onto the surface of the MnO2. That's why we have carried out the zeta potential analysis, where carbon dots show minus 10 uh, millivolt and MnO2 shows minus 1 millivolt. On addition of CD on the MnO2, the zeta potential of MnO2 has been just increased to minus 1.13. So this shows a successful formation of CD-MnO2 assembly. Now coming on to the fret. So again, the DLS shows 5 nanometers of for CDs and 211 nanometer for MnO2 nanosheets, and upon combination of CDs MnO2 we can see two peaks here. One peak, a very small peak which is around 5 to 6 nanometer, and there is a huge peak on 244 nanometer. It shows that the CDs, they are not only on the surface of the MnO2, there are also few carbon dots which are free in the solution. Okay, so next you can see the figure 6, where after addition of KMnO4 the fluorescence intensity of the CDs is being gradually decreased, and we have reported around 80 to 87% of quenching of the CDs on addition of KMnO4. And now, to understand whether the quenching is static or dynamic, we have carried out the lifetime study of the CDs and MnO2 conjugate. We can see the CDs has the lifetime of 4.56 nanoseconds, whereas the CDs MnO2 conjugate shows 3.48. This decrease in the lifetime, it proves that the CDs MnO2, they have undergone fret phenomena. Moving on, here in our sensing platform, apart from CDs and MnO2, one more important contributor is the concentration of benzoquinone. So to understand the optimization of benzoquinone, we have considered two different concentrations of E. coli. One is the very highest concentration, that is 1 into 10 raised to 9 CFU per ml. Another one is 1 into 10 raised to 3 CFU per ml. So with both of the studies, we have understood that the 4 millimolar of benzoquinone is optimum for the sensing system, and we also understood that just the CDs and the benzoquinone, they do not show any change in the fluorescence. That is visible in figure 9. And below we can see that even the system, the sensing system can be used for visual detection of E. coli. As the concentration of E. coli is very less, the color of the solution is almost the colorless. As the concentration increases, the color has turned brownish. Okay. So this shows the MnO2 plays a major role apart from CDs and BQ benzoquinone. The MnO2 plays a major role in the sensing of the E. coli. So now the main part, the detection of E. coli. So in CDs MnO2 sensing assembly, we have added benzoquinone E. coli incubated solution in a different concentration of E. coli from 5 into 10 raised to 1 CFU to 1 into 10 raised to 9 CFU. As we can see in figure 11, as the concentration increases, the fluorescence has constantly increased. This gave us a LOD of 50 CFU per ml. 50 colonies formation per unit per ml. And we have also done the selectivity studies for several bacteria like M. stigmatis, E. faecalis, S. aureus, B. cholerae, and P. aeruginosa, and along with the E. coli. Here we can see that only E. coli gives a highest response towards carbon series MnO2 assembly. Now further we have utilized the same sensing system for real sample analysis like rainwater, apple juice and potato, where we have seen almost 95 to 98 percentage of recovery for E. coli. These studies they show that our sensing system is highly selective and sensitive towards E. coli. Now the current word it revolves around the real time and on-site detection of the analytes. So because of the applications of these MnO2 or CDs and MnO2 platform, we have done a smartphone based image analysis. So here with the use of ImageJ software, we have for different concentrations of E. coli in presence of CDs and MnO2, we have done the image analysis to obtain a standard curve so that we can analyze any drinking water or the foods, the spoiled food for the detection of E. coli on real time. So in this, in a summary, we have developed a redox-coupled carbon dots MnO2 FRET-based conjugate for sensitive and selective detection of E. coli. It uses one of the unique enzymatic redox relay reaction which happens on the surface of the E. coli that is being exploited, and we have got a great results of a lowest LOD of 50 CFU per ml for E. coli. So apart from E. coli, if you see the third one, we have also published one of the paper on the basis of carbon dots and MnO2 for hydrazine. And during hydrazine, we have performed few of the experiments that gave us a lead for the detection of E. coli. So recently we have published this E. coli with the help of the same platform, that is CDMNO2. Thank you.
Thank you, Sharan.
Thank you. You can ask if you have any doubts.
Yeah, Sharan, I have some questions regarding is there any morphological studies that we have to perform for using carbon dioxide dots for selective analytes? Means apart from that you did morphological studies can be useful for this particular sensing platform or not? That I wanted to
No,
ask.
no, no. There is no need of any morphology here, because anyhow, we just require that the fluorescence donor CDs and the fluorescence acceptors MnO2, they should have highest efficiency. So if we can provide the highest efficiency of quenching, then we can get highest efficiency of fluorescence turn on. So maybe if you talk about the morphology of MnO2, yes, of course, if you give more surface area for MnO2 nanosheets, then more of the CDs will be on the surface of MnO2, then we will get more turn on.
Okay. Okay.
Yeah, but for the morphology, there is no need of CDs. But for MnO2 nanosheets, we have to have a larger surface area.
Okay. And another term that you have used, zeta potential. Means I have heard it. Means I just wanted to know what is this and how we should get it. from which instrument?
Okay.
That I want.
Okay, DLS and the zeta potential can be obtained from the same machine. So now this zeta potential, we talk about the surface charge. The surface charge for any of the material. Especially it should be a colloidal solution so that the Tyndall effect happens in the solution. That will give us the DLS as well as the zeta potential. And another thing is we cannot consider that whatever the zeta potential is there, that is fixed for one particular molecule or one particular material, because it changes according to the concentration of the material also.
Because in biology also people have used this zeta potential term for cell viability, means cell toxicity
Yes,
also
yes, yes.
they use.
Yes,
That's
yes,
what
yes.
I wanted to ask. Anyway, thank you. Very good presentation. Congratulations for your
Thank you so
publication.
much. Thank you. Okay, see you.
Sharon,
Yes.
here it is the only nanoparticles only, na? Carbon nanodots.
Yes, yes. We here carbon nanodots along with the MnO2 nanosheets.
Okay, okay. So here particle is any size dependence there or not?
Yes, we can go for size dependent CDs, but for our studies we don't require the size dependent of CDs, especially the CDs. But there are many studies which are being taken place on the size dependence of MnO2.
Okay.
Because as the size of the MnO2 nanosheets increases, the efficiency of FRET increases, and that will increase the sensitivity of the platform sensor.
Okay.
So as of now, for this particular work, we haven't done that size dependence. But of course, if we can monitor the size of the MnO2 nanosheets, we can definitely increase the sensitivity of the sensor.
Okay. Why should we use this benzoquinone? We can take any other
Okay,
molecule
now,
also or not?
yeah. Yes. Because this benzoquinone, see, this, on E. coli surface, the cell membrane, one special redox reaction take place, the 2-electron redox reaction. For that, here, the benzoquinone on the surface of E. coli, it reduces to hydroquinone.
Okay.
And next, the hydroquinone further reduces the MnO2. So it is a relay of redox reactions. One induces the other. At the end, it will give us the degradation of MnO2 as the fluorescence of CDs releases.
So benzoquinone itself it has the fluorescent activity.
Yes, no. Benzoquinone, it will go for only the redox reaction between benzoquinone and E. coli to give out the hydroquinone.
Okay.
Now this hydroquinone will reduce MnO2.
Okay. After that,
So when
carbon dots.
Yes. When this hydroquinone reduces the MnO2, the CDs will release into the solution.
Okay.
Now you can see the CDs. No, they have the fluorescence, but when they sit on the MnO2 nanosheets, the fluorescence is off.
Yes.
Yes.
After once
Now
reacted with E. coli, again give back
E. coli.
some. Yeah.
Yeah, this benzoquinone will turn into hydroquinone. Now this hydroquinone will break these MnO2 sheets.
Okay.
Then when they break the MnO2 nanosheets, the CDs, they will release into the solution. They will give back the fluorescence again.
Okay. So based upon that E. coli, and then it gives you some more concentration, means it will give you more bright of the fluorescent activity.
Yes, of course. That's what we have seen here in this figure 11. As we increase the concentration of E. coli, we can see the fluorescence has been increased.
Yeah, but here, did you check with anything with quorum sensing reagents? Means quorum sensing.
Like? Sorry?
Pseudomonas aeruginosa.
So we have taken few of the gram positive and gram negative bacteria. So here we have M. sphegmatis, E. faecalis, S. aureus, and V. calori, P. aeruginoso. So we have used these few of the gram positive and negative bacteria.
Bacteria.
Then we have compared the selectivity for the material.
Okay.
So
Very
there
nice
we
work,
can see
Sharon.
that in.
Yeah, because one of my senior work also related to quorum sensing.
Okay.
Here also we used to do these things only, where we are using that molecules. It will pinch the fluorescent activity. So that's why I'm asking here. Maybe have you tried with Pseudomonas aeruginosa or not?
No. We haven't. The other thing is, as we are for this particular selectivity, we have obtained these trains from the biology department. So, and there are also many restrictions on use of bacteria.
Yeah. Yes.
So, which are easily available, which can be easily handled in chemistry lab. That we have used here. But we
Yeah.
have covered both the gram positive and gram negative bacteria.
Yeah. Very nice,
Examples of
Sharon.
both positive
Yeah.
and negative. Yes.
Very nice, Sharon. Hey,
Sharon,
Thank
Aditya.
you so much.
I have
Yeah.
one
Yeah,
question.
sure.
I have
Yes,
one
yes,
question.
yes, yes.
Did you have covered the time dependent studies means so response time? Is it
Yes. Of course. Our very first study should be the time dependence, but we should understand that how much time these bacteria take to react with the benzoquinone to
ah
get back the hydroquinone.
that's
Yes, we
why
have done that. Yes, we have done that, and we understood that it requires 30 minutes of time to
okay.
convert the benzoquinone to hydroquinone.
Okay, fine.
So I haven't shown this here, but yes, we have done the time dependent study to understand when we'll get the maximum response for one particular concentration.
Sharon, means there is another question related to
Mhm.
benzoquinone. Means
Yes.
DDQ is also a benzoquinone form, a benzoquinone
Okay.
derivative we can say. So
Yes.
can we take that DDQ molecule and that will convert to hydroquinone and that reduce the MnO2 means to improve the response time of your fluorophore
Mm-hmm.
whatever system you have
Okay.
platform you have created. So for that means
Uh-huh.
I just wanted to ask means is it possible? I think because anthraquinone and with the anthraquinone and DDQ both can be used
Yes.
for this particular thing.
Yes. Yeah. Okay. Correct. The other thing is,
Hmm.
as we increase the aromaticity of these molecules,
Okay.
the bacteria will will react less
Okay.
with the as we increase the aromaticity. So
Okay.
that's why we, and another thing is we also have to uh, keep a check on the cost of detection.
Sure. Sure.
So even though when we at the end if we want to make a sensory tool, on-site detection tool for these E. coli, then we have to go for a very cheaper and which is also be used repeatedly. So you can see
Uh,
here in this figure only this benzoquinone, which has been
hmm.
converted to hydroquinone,
Hmm.
again reacting with the MnO2, it is coming back to benzoquinone.
It's a kind of cycle means
Yes, it's a
cycle.
kind of cycle, so that we can give you this cycles, or we can use it many times for the
Okay.
on-site detection. That was our
Okay.
main motto,
Okay.
to have an on-site detection tool. So that's how we have specially used benzoquinone.
Thank you very much. Thank you. Very
Thank you,
good presentation, yeah. Very good presentation.
thank you so much.
Aditya, Satya, you want to ask anything, people?
No.